In this example, we're going to try to factor a cubic polynomial. And we are going to use the fact that if we know a zero of this function, we have access to a factor of this function. There are two ways to have access to one of its zeros. Maybe you're given the graph of the function, and then you can just look at the x-intercepts, get the factors using the x-intercepts. But here we're going to try to be lucky. Okay, so we're going to try to find those zeros by trial and error. Okay, so what I'm going to do is calculate, f of some numbers. Now in the book they tell you which numbers to try, so I'm not going to get into the details of that. So for us, we're going to hope that the teacher has chosen like integer zeros that are not too large. So I'm going to try -1 and see if that's a zero. So this is 3 times -1 cubed is -1. -1 squared is 1. Times -1 minus 4, and let's calculate this. This is -3 plus 5 plus 4 minus 4, and no, I'm not lucky. This is actually equal to 2, and this is not 0. So here, okay, I just wasted a good 30 seconds, and I could calculate f of 0, but that's kind of obvious. F of 0 would be the constant term, so still no luck here. Maybe f of 1. If it doesn't work for integers, I could always try maybe a half or something like that. F of 1 is 3 plus 5 minus 4. Minus 4, and hey, hang on, that's 8 minus 8. That's 0. So here, okay, we've got a 0. So that means that x minus that 0 is a factor. Aha! So how do we factor with that now? Well, I'm going to divide my polynomial by that, because I know it divides evenly into by x minus 1. So divide f by x minus 1. So this is what I want to do now. So 3x, actually no, I'm going to need some space above it. So 3x cubed plus 5x squared minus 4x minus 4. I could have always tried like factoring by grouping, by the way. I didn't try that, but that would have been an option. Maybe it works, maybe it doesn't. Okay, because I have 4 terms. That would have been another option. Okay, I was just thinking about that right now. I thought I'd mention it. X minus 1, I divide by that. X goes, well, I need to multiply it by 3x squared to fit it into 3x cubed. So this is 3x cubed, and 3x squared times minus 1 is minus 5 minus 3x cubed, sorry, 3x squared. Okay, I'm going to get this right. 5 minus minus 3, that's 8x squared minus 4x. X times 8x will give me 8x squared. Now I subtract. Minus 4 plus 8 is 4. X times 4 is 4x. And bring down the minus 4, and bingo. Of course, I'm expecting to get a remainder of 0. But what I get from this is the quotient, okay, which tells me that f of x is x minus 1 times this quotient. Okay, so I've partially factored f now, and the quotient is a polynomial of degree 2. So now I can attack it with all the tools that I have for factoring polynomials of degree 2. So now I'm going to try the AC method. So product of 12, right? And sum of 8 is what I need. So that's 6 and 2. Whoa, perfect. So 3x squared plus 6x plus 2x plus 4. So I split my middle term. Now I factor by grouping. I get a common factor of x plus 2. 3x plus 2, and now it's fully factored. Okay, which also shows you that if I would have tried minus 2, I would have had a 0. Okay, So if I would have started with f of minus 2, I would have had 0 again here. So knowing, and then that could have been also the first factor that I would have used to divide f of x. So that's fully factored. So this is my answer. It also gives me access to information about the graph of f. So I know what the x-intercepts are. So even though that's not part of the initial question, let's keep going like this. I can have access to the x-intercepts easily. The x-intercepts are what? 1, 0, minus 2, 0, and 3x plus 2 is 0 at minus 2 2/3. Okay, so I've got 3 x-intercepts. I've got some, of course, I always have a y-intercept because the domain is all real numbers all the time for polynomials. So the f-intercept is f of, well, the y-coordinate is f of 0 and f of 0. Maybe it's easier actually to not use the factored form but the expanded form. So if I look at this, f of 0 is going to be the constant term. It's minus 4. So that means that 0 minus 4 is the y-intercept. Those are the x-intercepts. And from this, I could recover part of the graph. Not entirely the entire graph, but part of it. So let's say this is 1. 2 would be minus 2, 0 would be here. So this would be 1, 0. Minus 2, 0. Let's say this is minus 1. And let's say this is minus 5 here. So minus 4 would be the y-intercept. Minus 2/3, 0 is the other. This is minus 4, 0 minus 4. Whoop. Okay, and from this I could recover part of the graph. Oh, part of the graph. How did the graph look like at infinity? The end behavior. This is also the other stuff I can look at. End behavior. Okay. Well, let's look at the leading term that it will tell us about the end behavior. The leading term is what is it again? 3x cubed. 3x cubed. Now x cubed looks like this, and the 3 won't change the shape of the graph. So I know that it's going to end up here at infinity and here at minus infinity. So the graph is roughly. So if you use a decimals, you'll see that there's a minimum just before 0. This is something we don't know actually from the information we've gathered. So what in calculus we'll be able to figure out where the maximum lies. But all the other features of the graph, we can actually recover it from our analysis. So that's it.